this talk?
No.
Was it a W?
Basic error.
Basic error correction, yeah. So the kind of error correcting I'm doing there is a little bit of a special case, but I just want to point out this is at the a great example of an applied math type topic. It's really, it's also a discrete math applied topic. This is very pragmatic, real world stuff. If you use a cell phone, you're using error correcting codes all the time. Usually, I've always thought of error correction as something that takes place when you are transmitting things over the airwaves. Right? You're transmitting data over either a wire or a radio. But you can also think about things that are being written down, recorded for later use, and are subject to degradation over time. Right? I mean, you know, historians of math probably deal with this all the time. Somebody wrote something on papyrus 2,000 years ago, and now you've got to try to read it. The information content has been diminished as the years pass. Things like CDs and DVDs, you know, people put their grubby fingers on them, and you get fingerprints on the what's supposed to be a shiny metal surface. And so memory, computer memory is an example where if you don't have error correction, it's probably not going to work right. Because I mean, memory cells, solid state memory has gotten to the point where it's literally just half a dozen atoms holding a single bit of data. And you know, the least little infringement, a little cosmic ray coming near that chip is going to switch the bit states. My favorite is deep space communication. That's kind of a cool thing. The older missions that went off to explore deep space had things on them called snap reactors, which are magnificent but scary devices. They take a radioisotope like plutonium, which is decaying and generating heat. And because it's decaying, it's something that's decaying quite rapidly, so a good bit of heat is coming off of this radioisotope. And you can use heat to make power. You have a thermocouple attached to a hunk of something severely radioactive. Now imagine what you're thinking about when you go to launch that into space. I really hope there's no crash, right? I mean, if the rocket blows up, I'm going to be spewing intensely radioactive material all over southern Florida. So it would be bad. Nowadays, they use solar panels for most of the probes that go out there. But you know, if you're going to Pluto, as our society recently did, there's not a whole lot of sun out there, so you can't really use solar panels for that. So the upshot is, no matter how you get power in deep space, it's going to be a limited resource. So when you want to take a picture of something and radio that back to Earth, it's with a very low power transmitter, and it's in the presence of an enormous amount of interference. You know, the sun is a freaking nuclear reactor going off, a fusion reactor going off near us all the time. So yeah, if you didn't have error correction, you'd never get pictures of like Jupiter. That's the great red spot on Jupiter, taken by, I forgot the probe's name. This is an old one.
Voyager?
No, Voyager went off into deep space. It just did a flyby of Jupiter to get a gravity assist. We sent a couple of probes to Jupiter.
Was it Viking?
Viking is Mars.
No.
Is it named after one of the moons of Jupiter?
No? It'll come back to me sometime this evening, and I'll send everyone an email. So, you know, Dr. Kerrigan did a very nice talk about design theory, a series of talks about design theory. And I feel like I'm the one to come in and just be comedic levity, comedic relief, is that what it's called?
Yeah.
So I think this is funny because it illustrates a part of the point of error correction as regards natural language. This is a funny little essay that was published 150 years ago, and it was usually attributed to Mark Twain, but that's not the guy. And another memory failure, I'm forgetting who it is, in fact. But it's interesting to try to read this, because what they do is improve, quote unquote, improve the spelling in English as you go. So everybody can read the first sentence. For example, in year one, that useless letter C would be dropped to be replaced. Okay, so you can see how the C is going now. They're replaced by either K or S, depending whether it's a S sound or a K sound. Likewise, X would no longer be part of the alphabet. What do we need X for? Really, I see the point there. The only case in which C would be retained would be the CH formation, which will be dealt with later. So far I can read it okay, right? Year 2 might reform W spelling so that which and one would take the same consonant. Notice how consonant has got the K instead of the C now. While year 3 might well abolish Y, replacing it with I, and year 4 might fix the GJ anomaly once and for all. Can we read that so far?
Fix.
Generally then, the improvement would continue year by year, with year 5 doing away with useless double consonants and years 6 through 12 or so modifying vowels and the remaining voiced and unvoiced consonants. Can you still read that part?
Yeah.
By year 15 or so, it would finally be possible to make use of the redundant letters C, Y, and X, by now just a memory in the minds of old dotterers, to replace CH, SH, and TH respectively. Finally then, after some 20 years of orthographical reform, we would have a logical, coherent spelling in use throughout the English-speaking world. By the end, right, it's just ridiculous.
Yeah, that last line's the kicker.
That's the kicker, right, where the X's are TH's, and it took me a while to get to the point where I could read this. And why we don't have logical, coherent spelling in the English-speaking world is really my point here. If you make single errors in that stuff, you won't be able to figure it out. And if your eye will make errors sometimes, right? So it will really reduce the ability to read and write and speak and, well, mostly read and write English language. So there's something to do with what they pulled out here. There's a lot of redundancy that's in the language. Well, if you don't have it, you have problems. So let me get into the more mathy thing and stop trying to be funny. We generally are thinking about this setup. You've got someone who's sending data, something which could just be time, but sometimes it's radio waves, sometimes it's wires that represents the channel, and then somebody who's receiving the thing. So what we just saw in the title was a bunch of the letters were X'd out. That's called an erasure channel. This is really the more typical thing people, at least in the coding theory that I deal with, is the binary symmetric channel. So first of all, it means the data that's being transmitted is binary, zeros and ones. And it's symmetric. Oh, yeah, I said that. It's symmetric because it's equally likely for a 0 to turn into a 1 or a 1 to turn into a 0 as you transmit it. Now, in truth, that's not always the case. I think I mentioned that. There's other channels that are in wide use. So a non-symmetric channel, for instance, would be what you need for computer chips. The memory chips have a much greater probability that a 1 turns into a 0 than a 0 suddenly becoming 1. The 1 turning into 0 is just a little bit of charge leaking away, whereas 0 turning into 1 is charge materializing out of nowhere, which is less likely. It can happen with cosmic rays hitting a chip. So that's one of those useless diagrams. I already said this, but that's the setup. You have a sender, you have some transmission channel, and then a recipient. The thing is, in the transmission channel, errors come in. So when we're talking about binary schemes, the way to think of that is you've got a vector of zeros and ones, that's your message, and you can add a binary vector of error stuff to it. And that's what the channel does. The channel has errors in it that it throws at, that it adds to the message. M, well, these are typical abbreviations. M for a message, E for an error. The received message is R, which is M plus E. Now coding theory has to pop in here too. So what I was just describing is any channel. It could have been tin cans with string between them, and me and Clay is the ones that are message sender and receiver. But here we're getting more technical. We're adding some steps in here where between the sender and the transmission, before you send it, you encode it. And that's going to be where we throw in extra redundancy. You send the thing, and then you should be able to decode, and the composition of these three maps here should end up being the same as the original sender to receiver, except errors get corrected. So a not very useful, but a good example of an encoding scheme is triplication. In computer science, they sometimes have a tell me 3 times sequence. Like if you're doing something important, like it might wipe a disk, for instance, in a kernel operation, it'll run the same it'll run the same operation it'll run the same operation twice in the sandbox and then actually do it. So it wants to, you want to verify that you really meant it. So triplicating, can you read it if you triplicate the symbols in a bit of text? Yeah. It's not so bad. I mean, it's not trivial, but you can do it. You should notice that code, triplicating all the symbols, well, I just did it twice. Try coding this one. That's certainly mine. There's an error in this group of three, but what do you think is most likely? Life. My life would suck without you. That was a song lyric. 10 or 12 years ago, I forget. Who did that? So you guys all know. But this next group of things has a burst of errors in it. Can you notice where the errors are? My and life are still good. Would has DDE, but that's not so bad. S has, a couple of those S's have turned into R's, so now we've got my life would rock without you, which is sort of the opposite sentiment. My point being that a small number of errors could change just a few of the symbols and totally change the meaning of the message. So this is kind of bad that a burst of errors. There are special codes that deal with bursts, by the way. The code that's used for a CD or a DVD has to deal with burst errors because when you put your fingerprint on that disk, you erase 10 or 12 bits in a row, right? So, well, it could be hundreds of bits in a row depending on how grubby your fingers are. And that's a burst of errors. So the disk actually has the compact discs and DVD discs. I don't know how Blu-rays do their encoding, but I'm sure it's similar. They spread any one piece of data around on the surface of the disk. So that it's as if you had to read a bunch of things at once. This is why they need to buffer for a quarter of a second, half a second before they actually display. So yeah, this triplication can handle some things, but it's not going to work for everything. There's no one code that'll work for all possibilities. So now, with this new setting of encoding and decoding, we've got some extra terminology to talk about. M is still the message. We usually use C for the encoded message. E is the error vector like before. R is what's received. That's a coded message plus an error vector. And then M prime is the decoded message. You're just really hopeful that M and M prime match. And you can only control this up to the sort of probabilities. You can't be perfect necessarily. So where did all this get started? People have heard of ASCII, I assume. When somebody talks about a text file, they mean it's ASCII data in the file. That's pretty old. It stands for American Standard Code for Information Interchange. And it uses the numbers from 0 to 127 written in base 2. So that's strings of length 7 in binary data. And that gets you everything on the keyboard, lowercase, uppercase, all the characters, the funny stuff, plus a couple of things like ring the bell is one of the ASCII characters.
Yeah, so how do you get all the ASCII art if you only get what's on the keyboard?
ASCII art is when you make art out of the symbols that are just on the keyboard. It's like making those emojis that people all like to use. The emojis originally started with things like semicolon, dash, parenthesis, which if you look at it sideways looks like somebody winking and smiling. Right? But then now the apps everybody uses converts that kind of a key sequence into a little picture of a face with winking and smiling. Right? But the original emojis were just text, and that's really what ASCII art consists of. Is text. So, wait, too fast. Oh, maybe not. I guess I just put this picture in because I thought it was cool. This is a teletypewriter. You see the lady seated, and the one over her have I believe those are Air Force insignias on the sides of their shoulders. So these were wax Women's Air Corps. This was before there really was an Air Force, so, you know, this is World War II. I think these ladies are on loan to Bletchley Park. So the point is they were receiving Morse-coded messages over the airwaves and writing them down by hand, and then somebody would take them and type them into a thing, and they could put it into computers for use in the decoding machines. So that's just a weird little bit of history there. So back to the ASCII. The 7 bits handles the character strings that we need, the total set of 127 symbols. Somebody said, well, we could just have one more bit. And 8 is kind of nicer. And then add, they call it a parity check bit. So what you actually do is this. You count how many ones you've got in one of these messages. And if it's odd, the parity of that whole message is odd, you're just going to add one, you'll add an extra 1. If the parity that you calculated from the first 7 is even, then you don't have to do anything. So the parity check bit would be 0. But after you're done adding a parity check bit, you're going to have even parity. There will be an even number of ones all told. And that's kind of useful. If you end up, well, that is true. 8-bit bytes come from ASCII and the fact that they threw in a parity check bit. But if you get a message that's got like 7 ones in it, it couldn't be right. You're only going to have messages that have an even number of ones if no errors are occurred. This is still a part of the TCP protocol for internet communication. There's a signal to say, whoa, I didn't get that, or I think there's an error, send it again. So retransmission is always an option. This is what makes, you know, internet communication sometimes take a lot longer than it feels like. Not that the time between your station and who you're receiving the data from is not that great, but that the staticness of it is that great, and you're having to ask for a lot of retransmissions at a sort of machine level. So this is going to make Ray excited. We're going to talk about symmetrical probabilities. So suppose you've got a transition probably fairly large. 5% of your bits will get changed from 0s to 1s and 1s to 0s. That's a pretty large amount. We call that a pretty noisy channel. Here's the estimator of fault-free communication, using, thinking about the binomial distribution. Basically, if I have no errors, perfectly good, I'll have fault-free communication. If there's a single error, I'll be able to actually at least tell that I've got an error and ask for retransmission. But notice what happens if there's 2 errors.
You're not going to ask.
I'm not going to ask, and I'm going to get a character that's wrong. I'm going to think it was transmitted properly, but I won't be able to correct it. So what you can get then is HU 0, so no positions are in error. 0.95 is the probability of correct transmission, so that's to the 8th power. And 0.05 is the probability of incorrect transmission, or that it gets switched. That's the, well, anyway, and then this is HU's 1, that's 1 error. 7 bits were correctly transmitted, and 1 bit was transmitted falsely, or in error. So that comes out to 0.94, that's great. So the probability that you'll be able to, well, you know, it's a little bit, it's quite close to the 5% that turns out that is the transition property. People often use that as an estimator.
If you had 3 errors, wouldn't it send back and say there's an error? And then you get the correct?
Yeah, that's actually
a little higher than.
So hopefully that'll be very good. If you in fact have any odd number of errors, you're going to ask for a retransmission and hopefully get the right thing back. Although you may be amazed. You're like, I asked for retransmission of this and I got that. You may question whether the new thing is right too, because they'll be rather different. But if you throw in all the odd errors into the probability, it hardly changes the final sum at all. 0.948 now, what was it, 943 before? The reason is getting 3 errors, where 95% of the time you'll have no errors, that's pretty unusual. So that having, in this binary symmetric channel, bursts of errors like that usually don't happen, they're quite rare. Okay, so what's an error correcting code? There's sort of 2 viewpoints. I take the viewpoint that I stated here, that it's a subset of a set of possible messages. The other take on this is it's a way to send messages to things that you'll transmit. So it's the encoding process that describes what an error correcting code is. That's a broader approach. But basically, if you just think of it as a set of the potential binary vectors that one might send, that's a good way to deal with it. So practical consideration, you ought to be able to distinguish the code words, the things that are actually usable for transmitting messages, from things that aren't code words. So I'm just going to quiz you on the triplication code here. Which ones of these are code words? If triplicating the digits or the symbols is our thing.
First one.
Cat, right? Is code word.
Sure.
That's 3 A's followed by 3 A's. And if you play Scrabble, that's one of the 2-letter words that's very important. That's a type of lava, a type of rock. The Hawaiians have a lot of different ways to say volcanic rock, and that's one of them. What about aardvark?
No, enough A's.
Yeah, right. The first symbol is a single A, and it should have been triplicated, so it didn't have a chance, really. In fact, one way you can tell with the triplication code is you ought to have a multiple of 3 number of letters, and aardvark doesn't. Everything with the A is triplicated. I was wondering if the middle thing with the 6 A's would throw you off, because it may be a properly encoded code word, but most people don't think that AA is a reasonable word.
It's not a cast now.
Huh?
I was ready to go.
Oh, yes. Maybe it means come on. No, I'm sorry. I'm just not going to start quoting Monty Python anymore.
Makes more sense of friends.
So now I'm going to ask you about ASCII. This is harder. Get your binary thinking caps on. Are these code words in extended 8-bit ASCII?
The first one I see.
The first one's not?
You have
I
any
see
number
4
of
ones. Even number of ones. It's good.
Last one has an odd number of ones.
Yeah, so if a single error happens, can you tell what we should change there? It feels like it, right? But I can actually change any one of them.
Yeah, it doesn't
Right?
matter.
If I made that a 0, then I'd have 6 ones, and it would be good. And so you can actually change any digit. The problem is this ASCII sending with the error bit added in. Sorry, not error bit, what we call it, parity bit added in, just detects errors. It won't fix them. So what we really want is to fix and have an automatic procedure for fixing errors. So whenever I talk about matrices, I always throw this slide up. Now it's really getting old, but I still love that movie. When I was in grad school, the movie was just coming out, and the Wachowski, how do you say it? Wachowski? One of those guys that came out. Right?
I have no idea.
You know all the trivia. Come on.
I don't know how to pronounce it.
All right. Well, the Wachowski brothers, I think, lived in Chicago. So that was where they had their original release. It was sort of the premiere of the movie. And they had this advertising campaign where these completely black billboards, utterly, flat black, in the middle of it, just a tiny little bit of text that said, in white, what is the Matrix? And people were like, what the hell is this? Everybody. But I was in grad school. It's like, I know what a matrix is.
It didn't say a matrix.
Yeah, I know,
It
but I
said
didn't
the
know.
matrix.
It kills the joke if I do. So we're going to actually think about this from the perspective of linear algebra. Almost all the students here have done linear. Yeah? Okay. So this will be a quick review. Conformability for matrix multiplication. So you've got an M by N matrix, kind of going graphically there, and then a P by Q matrix, and the answer is an M by Q, provided that the middle dimensions, N and P, are equal. Those have to be equal, and then the size of the results will be M by Q. Remember that? If you think of a received word as a vector, we're carefully going to choose a matrix. We call it H. So the matrix vector product, H times B, comes out 0, and then we'll know that B is a code word. So for instance, this thing, just a matrix that's 1 by 8 with all 1s in it, is the matrix version of the parity check thing we just talked about. See, if you multiply that matrix, 8 1s, with a column vector that's got 8 1s, or 8 bits in it, The dot product, really, of those things is going to count how many ones are in there. And it's all going to be done mod 2. We're working with binary stuff. So, it's going to be 0 if there's an even number of ones and 1 is not. So there, this is terminology, just really. You're going to multiply a matrix times a vector, and you'll receive, generally speaking, another vector. My last example was a single number, but generally speaking, that's going to be a vector. And that vector is called the syndrome of the receiving verb, so terminology. What we're usually going to do is say this: if the matrix takes a code word to a 0 vector, sorry, let me say that more smart-like. The matrix will take a code word to the 0 vector and non-code words to something else. So you're going to detect whether you've got an error or not. If you've got a code word, it comes out all zeros when you do the matrix multiplication. If it's a non-code word, you'd like that non-code word to kind of help you with the correction. This is what the term is, just that it's a syndrome. So the code I'm about to show you is created about 1950, after the World War II era, by Richard Hamming. He was working for AT&T Bell Laboratories at the time. And I guess it makes sense. AT&T was interested in communications. But at that time, all their communication stuff was analog. The telephone wires literally sent voltage that represented your voice across the wire. They also had telegraph, but that was, I mean, that's only a sort of a weak sort of digital. But they were looking to the future, and they were planning for digital communication to begin. So people think, nobody's really gotten a straight answer out of Hamming about what he was thinking when he came up with his first error correcting code. But I think probably he was talking about syndromes. He's passed away now. And I've met him in his older years. He was almost 90 when I met him. And he was suffering pretty badly from Alzheimer's disease, so he wasn't really forthcoming. But he was a genius before his brain rotted away. Anyway, I think he was thinking about syndromes. So I'm just going to ask this as a generic thing. How big do the syndromes need to be so that I'll be able to distinguish errors in an ASCII word?
Less than 8 bits.
Less than 8, yeah. I need to distinguish, I mean, think about where errors can happen. There's only 8 positions. So I need enough data in my syndrome to distinguish 8 different possibilities. Now, how many binary vectors are there of length 2, for instance? All zeros, that's code words. 1, 0, 1, sorry, 0, 1, and 2 ones, right?
Right.
So I got 3 non-zero syndromes. So that's not going to do it. If they're length 3, 2 cubed is 8, maximum is longer than that. So you'll have the 0 vector as a syndrome, and then 7 non-zero things. And if you're wise or you're clever, you can figure out how to use those 7 non-zero things to locate an error. But Hamming was pretty smart. Yeah. So here it is. Yeah. Okay, here it is. So what Hamming did was create a parity check matrix, as this is called. Notice that it's 3 by 7 in this case. 3 by 7? Oh, sorry, there's another one that's 3 by 8, 4 by 8. Anyway, this one is going to be appropriate for length 7 vectors, isn't it? Because it'll be 3 by 7 times 7 by 1 gives you something that's 3 by 1. And do you notice what the columns of this matrix are?
What the errors are.
Yeah, those are. If you can read binary, they're binary. That's the binary. 001 is 1. 010, that's like 10 in binary, is 2. 011, 11 in binary, but that's 3, 2 and 1. That's 4, 5, 6, 7. So if you get the syndrome of a thing, it's actually going to tell you where the error is by literally saying what column is in error. So quick computation with matrices. Think about multiplying your H, think of the matrix I just did, times a received vector. But the received vector is really a code word plus some error vector. And matrix multiplication of a matrix times a sum of 2 vectors distributes. So you get H times the code word plus H times the error. Okay? But H times the code word is, by definition, 0. right? So this part's 0, and that part's h times the error vector. If the error vector has only got a single 1 in it, there's 7 of those, they're the standard basis vectors, right? They're the things that are all zeros except for a 1 in one position, for R7 in this case. And think about it, when you do the matrix vector product there, h times that error vector, it just picks out one of the columns of the matrix. So it reports as a syndrome what the column number where the error happens is. So yeah, because of that clever way of constructing the parity check matrix, this linear algebraic operation lets you compute the position of an error. So can you fix it now? This is cool. That it's not just detection. You can go, okay, I know the error was in position 6, and boom, put it switch to 0 to 1. Yeah, that's awesome. Now, do we have good error correction codes like this? I mean, this is a pretty small code, but this is sufficient to deal with no errors and a single error in any position and repair the damage. That's an argument. There's really been a lot of work done over the last 70 years, well, 67 years, I guess, trying to find good error-correcting codes and in more impressive schemes. Like what NASA currently uses for transmission of data from their space satellites, or their probes, rather, to send messages back. Instead of blocks of length 8, they send blocks of length 4096. That's a lot of bits in a row. It's a power 2, so they can divide it up into 8 chunks if they want. But they have an amazing code that was specially developed for space-based use. That's called a turbo code that takes those 4096 things and turns it into, I can't do it, twice as many.
Yeah. I was going to say, whatever 2 times.
It is twice. It doesn't have to be twice as many, right? It can have different amounts, but the particular turbo code they use actually treats the data as it's a stream, and the redundancy bits are interleaved with it. So you end up having twice as many bits in the stream as you start with. This is what we just did with defining the code in terms of that parity check matrix. I said we're talking about the set of vectors, so that a matrix H times the vector 0, V gives us the vector 0. But if you've done linear algebra, you've talked about null spaces of matrices before. That's what an error-correcting code actually is. So that means that the code itself is a space. This isn't just a set of vectors. That's how I define it, right? It's a vector space itself. And so it's a vector subspace of the potential, all the potential vectors of the given set. With the weirdness that you're almost all used to doing vector spaces where the real numbers are the field involved. But these are vector spaces over the field with 2 elements. So another perspective on essentially the same thing is to use the matrix that is a base, whose columns are a basis for the dual space, or the orthogonal complement. What it really amounts to is, I'd rather work constructively. Right? I'd rather have to say, here's a way to build these messages, rather than here's a way to check that they are a message if you got it. Right? So if you've got a constructive one, basically if you've got a basis for the space that the code words represent, you can present that in a matrix form. So that's called a generator matrix. And I usually think of it this way. I want a generator matrix to do encoding, because it'll let me take some random message and encode it into a particular code word. And then I want a parity check matrix for decoding. But the two matrices are very much related to one another. So this would be the generator matrix for the Hamming code. Notice its size is different. It's got 7 rows. I said that wrong. It's got 7 columns, but it's got 4 rows. Because the null space, wait a minute, does everybody know the rank nullity theorem? That's a good one for linear algebra folks.
Say it again.
It's called the rank nullity theorem. If you've got any matrix transformation from Rn to Rn, there's 2 numbers associated with the transformation. One is the dimension of the range of that transformation, the other is the dimension of the null space. So one's called the rank and the other's called the nullity. And they add up to n. So the generator matrix and the parity check matrix are showing you examples of this. The transformation is from R4 to R7, and its rank is 4. You're seeing how many rows there are. But the nullity of it as a transformation is 3-dimensional. That is why the parity check matrix has 3 rows in it. Okay, what have I done to that matrix? I had a lovely matrix up there that was supposedly the generator matrix for our code.
Your identity.
I've done matrix operations. Can you tell what you have? What matrix operations have I done? I'm allowed to permute rows, aren't I?
Yeah.
What does that mean in our setting? Permuting rows means, I think this basis element could be mentioned first. Why not? You know, that's just, changing the order in which I mention the basis elements. But I've also done things where I've added rows together.
So you got the identity.
Is it okay to add 2 rows together and get a new row?
Yeah.
As long as I don't keep all 3 of those things around, right? You've got to do what's called row replacement. There's also, let's see, row interchange, row replacement, no, row scaling. You know those 3 options? So row scaling, what would that amount to in binary? This is an annoying question.
Multiplying by.
Multiply by 1, you've got the same thing, or multiply by 0, you're not supposed to do that.
No.
It's not row scaling.
So scaling is pointless if you're in binary. That's weird. So this turns out to be an equivalent generator matrix that can be achieved just with the standard row operations. It's minus scaling, we don't need that. But there's another kind of operation one can sometimes do, which is permute the symbols, permute the order that the columns appear in. That is an interesting idea. It leads to a connection with error correcting codes and group theory. I'm going to probably lay off at this point, but there's some permutations of those columns that I could then do the row operations and end up with the same matrix. And there's others that that's not the case. So it means every one of these matrices corresponds to a permutation group in a very natural way. It's called the automorphism group of the code, which is probably where we'll start in 2 weeks, seeing a connection between the error correcting codes and group theory. Those are doing in abstract, but we'll enjoy that a lot.
From what we hear.
It's 500, isn't that what we're supposed to do?
Yeah. So I just have a quick question. What you chose a particular row operation so that there is, and you pointed out there's an identity in the first 4. So you use kind of a reduced row echelon type.
Why is this a good form?
Yeah.
It means that if I encode a vector, I'll be encoding something of length 4.
Yep.
I'll be able to read the first 4 positions.
Oh, yeah.
And then there'll be other jump.